Hello, welcome to this fourth week of lectures on radio astronomy. This week particularly we'll be focusing on signal processing and receivers. Now if you remember, we discussed in the previous weeks like the nature of the radiation coming from the sky, thermal and non-thermal origins. How do we detect and measure emissions from the sky, particularly in radio band, using radio telescopes? In this context we have done the antenna radiation fundamentals. We also studied key radiation fundamental quantities like specific intensity, flux density of the cosmic sources. In particularly, we understood black body radiation and the Rayleigh-Jeans limit. We also defined a few specific temperatures relevant to this particular course. One of them is the brightness temperature, which is a product of the Rayleigh-Jeans limit, directly proportional to the specific intensity. The sky temperature in the same line, the antenna temperature, and the noise temperature. The noise temperature here quantifies the amount of noise in a system, and the sky temperature or the brightness temperature of the source quantifies the amount of signal present, and is the interplay between signal to noise. And if you remember that because we are dealing with very, very faint signals in case of radio astronomy, in fact, we define the unit of 1 Jansky to be 10 to the minus 26 watts per meter square per hertz. And the brightest radio source, like the sun in radio, is about 10 to the power 6, 10 to the power 8 Jansky, which still brings the amount to 10 to the power minus 20 to 10 to the minus 18 watts per meter square per hertz. So the strength of the radio signal which we are looking for from the sky are extremely faint compared to any other electronic devices which we're using day-to-day life, like our mobile phones or laptops, etc. So the principal criteria over here is to detect the signal coming from the sky in this radio band with a significant signal to noise ratio, with a amount of confidence that we can demarcate that as a real signal and not just another interference. So in order to do that, we have to build larger telescopes, more sensitive telescopes with sufficient resolution and collecting area. We need to ensure that the maximum power transfer happens by impedance matching. We just did in last week. And we also need to have larger bandwidth of observations. That means collecting more and more signals, and that means signal noise ratio goes up. That also puts the design specification on the antenna that it should be broadband. This is what we have done so far. What is this week's plan? This week's plan is to take you through a very basic blocks of signal processing. We know that in the beginning there is the antenna called feed here, but then there are several stages of amplification, mixing, IF amplifier, bandwidth, bandpass filter, square wave detector, and low pass filter and amplifier, where the entire signal goes through this particular chain and then finally gets recorded in a computer. So we will deal with different kinds of signals. We will touch in a very major technique called Fourier transform. We'll talk about block diagrams of receivers, connectors, adapters, attenuators, filters, mixers, switches, amplifiers, etc. How does a receiver is designed? We will talk about that, and finally sampling theorem. So that's all we are going to cover this particular week. To start with the signal, A signal is basically what is coming from the sky. So why do we need to? We already have discussed nature of the radiation by which the signals originate from the sources in the sky. But we need to understand what kind of signals we are looking into. What are the characteristics, features in time and frequency, so that we need to build an optimized receiver system to collect that signal. Like signal coming from a signal may be picking at a particular frequency. So to optimize the gain, we also need to design our telescope at that particular frequency. Suppose the spectral line is there at 1.4 gigahertz. We need to design a telescope which will operate at 1.4 gigahertz and not 2 gigahertz. Similarly, we know that the synchrotron radiation becomes more and more stronger at lower frequencies. So we need to collect that at a lower frequency. We would like to see the redshifted hydrogen signal from a particular redshift. So we need to build our telescope at a particular frequency band corresponding to that redshifted frequency. Now, some of this you may be familiar with, some you may not be familiar with. Don't worry, we will discuss as we go along. So anyway, for this particular discussion, we need to know the nature of the signal in order to make a receiver which can detect it more effectively. So anything we receive which can convey information to us with or without processing is a signal. For example, we listen to this particular lecture. You can perceive it, so this is a signal for you. More formally, we can define a signal to be an electromagnetic wave received over a period of time through an antenna, which is converted into electrical time varying voltages. Ideally, should only contain transmissions from the source under observation. However, because we receive any signal coming in that particular band from that particular direction, and it can be the sky signal which we desired to collect, but as well as we can collect some interfering signal which will be detrimental to our detection, and so that we have to remove from our data in order to detect the actual signal we wanted to collect in the first place. It is to be noted that it is not as simple to retrieve information from the received signal because it is contaminated by different noises, measurement errors, and interferences. So like as I said, there are radio frequency interferences. So we are collecting at a particular band, for example, say 1.4 gigahertz. But there can be spurious transmissions nearby, which also may come in the nearby frequencies, which can spill over because of non-ideal or imperfect transmission modes. And they create noise for our reception. So we receive the sky signal, of course, but we also receive, in addition, some spurious signals which are not from the sky, but mostly from the neighborhood and man-made. We will discuss and discuss natures of those kind of interferences one by one in future weeks. We need to understand that the different types of signals and characteristics before designing a suitable receiver for it. That's the reason we need to understand nature of the signals. Broadly, signals can be classified into 7 different types. Continuous time and discrete time signals. As the name suggests, continuous time is a continuously varying with time, and discrete time signal is discretized over time. Analog and digital signals. If a continuous time signal xt can take on any value in the continuous interval a to b, where a may be minus infinity or a finite start time, and b may be plus infinity within a finite time, then the continuous time signal xt is called an analog signal. On the other hand, if a discrete time signal xn can take on only a finite number of distinct values, then we call this signal as a digital signal. For example, a discrete signal, voltage versus time, can only have 2 volt, 3 volt, 4 volt values and nothing else. Real and complex signals, third type. A signal xt is real if it's real valued. It's complex if it is composed of complex components, both real and imaginary parts. Deterministics and random signals. Deterministic signals are those signals whose values are completely specified for a given time, and random signals, it has to be stochastically determined or statistically characterized. Even and odd signal. Signal xt or xn is referred to as an even signal if x minus t is equal to x of t, or x minus n is equal to xn. A signal is referred to as odd if x minus t is equal to minus of xt and x minus n is equal to minus of xn. It is a fact that any signal xt or xn can be expressed as a sum of two signals, one of which is even and one of which is odd. So, in general, they are characterized by sum of odd and even signals. One can define even parts as half of xt plus x of minus t by 2, and in this case xn and x of minus n by 2, and similarly the odd part. After that, there can be signals which are periodic and non-periodic. A continuous time signal x of t is said to be periodic signal with period t or n if there is a positive non-zero value t or n for which xt plus mt is equal to x of t. So if the signal repeats itself in value after a certain period, then it can be called as a periodic signal. If not, then it is a non-periodic signal. Energy and power signals. Instantaneous powers Pt or Pn is defined as P of t proportional to xt square, and P of n is xn square. Then energy signal can be given as a total normalized energy content, and power signal can be total finite normalized average power given by this. So those are the basic signals in which we know of. So whatever we will observe from the sky will be classified in one of them, and that way the operations becomes easier. So how the basic signal operations defined? In general, there are two parameters for an electrical signal: amplitude and time. So one can perform several operations in amplitude as well as time, like amplitude scaling, addition of two signals with corresponding amplitude, subtraction of two signals, multiplication of two signals, time shifting, shift the time. So x t plus t naught is negative shift or delay in time or delayed time delayed signal, and xt minus t naught is a positive shift or advancement in time or time advanced signal. Time scaling, x a of t is a time scaled version of the signal x of t. A can be greater than 1 corresponding to compression of signal, less than 1 corresponding to the expansion of signal. Time reversal, x of minus t is the time reversal of the signal x of t. Even though this concept might seem irrelevant to the students who are motivated to radio astronomy data analysis, these basic concepts play a major role in understanding what we teach next, which is Fourier analysis. That's why these basic constructs can really help you to go forward with the Fourier series and Fourier transforms. So signals we defined. Now we define what is a system. A system is a mathematical model or a physical process that relates the input signal to the output signal. In that case, even a radio telescope is also a system, because there is an input signal which is coming in, receiving in the front, in the antenna, and it passes through a lot of processing and finally gets out and recorded in the computers. So this whole block is a system. Even the individual blocks are also subsystems which play their own role. Let X and Y be the input and output signals of a system. Then the system is viewed as a transformation or mapping of X into Y. So X is the input, Y is the output, H is some kind of an operator which is defining the system, which operates on the signal itself. Either receives it, amplifies it, or does some operations like filtering, mixing, etc., which will come soon. Okay. There are different kinds of systems: deterministic and stochastic systems. If X and Y are deterministic or stochastic signals, the system can be continuous time and discrete time systems, where A and Y are continuous or discrete time signals respectively. Systems with memory and without memory. The system is said to be memoryless if the output at any given time depends only on the input at that particular time, and it has no other memory. Then the system is called memoryless. And otherwise, system is supposed to have a memory. So let's see what a memoryless system looks like. For example, Ohm's law, where the voltage, which is the output, is proportional to the input current and linked with the system of the resistance. So the R here is like an operator which takes the input signal IT and transforms that into a voltage V, which is a function of T. But the I voltage at a given time depends on the current at that given time only, and not at a previous time or at a later time. That's why this system is called memoryless. Correspondingly, if I introduce a capacitor instead of a resistor, in a capacitor, we know it charges and then discharges. So current flowing through it charges, and then it doesn't flow, it discharges. So that itself has a memory, which is a memory from the past. So it depends on the time, also in addition to the current time, it also depends on the time which has passed. So that's why it is a system which refers to having a memory. Causal and non-causal systems. A system is called causal if its output at the present time depends on only the present and or past values of the input. Thus, in a causal system, it is not possible to obtain an output before an input is applied to the system. A system is called non-causal if its output at the present time depends on future values of the input. Example of non-causal systems are yt is equal to xt plus 1, or yn is equal to x of minus n. So all memoryless systems are causal, but not vice versa. That's the definition of all the systems we will be coming across. Continuing that, we define something called linear and non-linear systems. If H where H is the transforming the input signal of X into output signal of Y. If H satisfied the following two conditions, like additivity, H of X plus X1 plus X2 is equal to Y1 plus Y2, and homogeneity or scaling, H of alpha times X is equal to alpha Y. Then H of alpha X1 plus alpha 2 X2 is equal to alpha 1 Y1 plus alpha 2 Y2. If these two conditions are satisfied, then H is called a linear operator. And a system represented by a linear operator is also called a linear system. And if it is not, then it's called a nonlinear operator. Okay. So supposedly H of X1 plus X2 is Y1 plus Y2, and H of alpha 1 X1 plus alpha 2 X2, where alpha and alpha 2 are just scaling, is equal to alpha 1 Y1 and alpha 2 Y2. Then H is called a linear operator or also a linear system. If not, then it is called a nonlinear operator or nonlinear system. The next in the definition of systems are time invariant and time varying systems. A system is called time invariant if a time shift in the input signal causes the same time shift in the output signal. So if you have H of xt minus tau, that is giving of y of t minus tau. This is called time invariant, and if it doesn't satisfy this link relationship, then it's called time varying. Linear time invariant systems, or LTI, is a system which is linear and also time invariant. Then it is called LTI, or linear time invariant systems. In addition to this, we know about stable systems, which system is bounded input, bounded output stable. If for any bounded input x defined by modulus of x is less than or equal to k1, the corresponding output y is also bounded defined by the same y less than or equal to k2. Here k1 and k2 are finite real constants. An unstable system is the one in which not all bounded inputs lead to a bounded output. Last one, feedback systems. A special class of systems of great importance consists of systems having feedback. In a feedback system, the output signal is fed back and added to the input system, like this. For radio astronomical applications, we will restrict our discussions to linear and linear time invariant system, as a system designed for reception of radio waves are linear systems. So the next topic for today's lecture is Fourier series. So we will try to introduce the Fourier series and then gradually move over to something called Fourier transform. So Fourier series, as you know or may know, that it was developed by Jean-Baptiste Joseph Fourier. This is the continuous Fourier transform is important in mathematics, engineering, and physical sciences. It is probably the most useful tool for data analysis in engineering. Its counterpart for discretely sampled functions is discrete Fourier transform, which is normally computed using so-called fast Fourier transform. The DFT has revolutionized modern society as it is ubiquitous in digital electronics and signal processing. It is almost everywhere in signal processing, sound processing, image processing. Lots of imaging techniques are based on radio Fourier transforms, like radio interferometric imaging, spectral information in astronomical signals, developed by Fourier transform, Fourier spectroscopy, spatial features in signals from early universe, power spectrum, bispectrum, etc. are all developed based on this single piece of work called Fourier transform. And Fourier series leads to that. We'll come in a bit. Radio astronomers are particularly avid users of Fourier transforms because Fourier transforms are key component in data processing, periodicity searches, and instruments. And they are the cornerstones of interferometry and aperture synthesis. So, to summarize, Fourier transform is a very important tool, not only in radio astronomy, but also for electrical and communication engineering. So a lot of signal processing tools arises from Fourier transform are based on it. Before we jump to Fourier transform, let's first start with the Fourier series, as we said. So we represent any periodic signal xt. Joseph Fourier developed an expression called Fourier series. This is in terms of an infinite sum of sines and cosines or exponentials. Fourier series uses orthogonality condition. Fourier series representation of continuous time periodic signals. So a signal is said to be periodic if it satisfies the condition x of t is equal to x of t plus capital T, where t is the time period, capital T is the time period. Similarly, in discrete signals, x of n is the x of n plus capital N, where n defines the period. There are two basic periodic signals, sines and cosine, and also complex exponentials. The signals are periodic with period of t. Capital T is defined by 2 pi over omega naught, where signal itself is xt is defined as cosine of omega naught t, or xt is defined as e to the power j omega naught t, where j square is equal to -1. A set of harmonically related complex exponentials can be represented as phi of kt, which involves e to the power j omega naught t, or that omega naught can also be represented in terms of capital T by k times 2 pi over capital T. So k can take any integral values, positive or negative, and 0. According to the orthogonal signal space approximation of a function xt with n mutually orthogonal functions is given by x of t is summation over k goes to minus infinity to plus infinity ak e to the power jk omega naught t, where ak is the Fourier coefficient, also known as the coefficient of approximation. The signal x of t is also periodic with time period of capital T. This equation represents Fourier series representation of periodic signal xt. The term k is equal to 0 is a constant, plus minus 1, having fundamental frequency of omega naught is called the first harmonic, plus minus 2, having twice omega naught is second harmonic, and so and so. So the nth harmonic is k is equal to plus minus n. So you can represent x of t, a periodic signal, in terms of infinite sums of periodic cosines and cosines. So any periodic signal then can be decomposed into this summation over sines of cosines. That's the Fourier series. Supposedly given a function, then how will you derive this Fourier coefficient? Because that is the only thing you have to figure out in order to do the representation. So then what you do is, if you simply go from here, you simply multiply by e to the power minus j, the conjugate of this exponential term, on both sides, you get x of t e to the power minus j n omega naught t, and this side you basically end up being having a of k, because this cancels out. Okay, hence you essentially then do integral on both sides for, sorry, it doesn't cancel out, it's k and this is n, so k minus n term survives, sorry. And so if you integrate over both sides, the a of k is independent of the variable t, so that comes out of the integral, and the inside term is which remains is e to the power j k minus n omega naught t, okay, 0 to t. So you basically, let's go back and start again. So you have this function x of t given in some summation over k goes to minus infinity to plus infinity, a of k, a k e to the power j k omega naught t. You simply multiply both sides by e to the power minus j n omega naught t, and so it is and then you do a integral on both sides from 0 to capital T. On the right hand side, left hand side, this thing remains as it is. On the right hand side, you can see that ak and the sum is a function of k and not t, so they come out of the integral, leaving inside the integral the integrand e to the power j k minus n omega naught t. Now you can write e to the power j theta in terms of cosine theta plus j sine theta. That is Euler's formula. If you do that, then this is the, you come up with e to the power j k minus n omega naught t is cosine of k minus n omega naught t dt plus j the sine integral. We also examine that if k is equal to n, then this integral goes to t. If k is not equal to n, then this goes to 0. So we go back to that main equation, and then we just put k is equal to n. So a n t, the right hand side reduces to a n times t, and the left hand side is still that integral. So a n can be written in terms of the left hand side integral and capital T. That's how we get the value of AKs, which is done in the same way. K and n are just arbitrary numbers. So we do that, and that's how we evaluate the coefficients of the Fourier series. Now, just take an example. So how do you understand Fourier series? So you can take an arbitrary function f of x, okay, defined within the interval of minus 0.5 to plus 0.5, and it can be represented by the series expansion of a0 by 2 plus minus, summation over n equal to 1 to infinity an cosine of 2 pi nx plus bn sine of 2 pi nx. Okay. In this particular case, an and bn are can be represented in terms of the function fx, the similar way we are evaluating the Fourier components in the previous example. And the set of basis functions cosine 2 pi nx and sine 2 pi nx are actually orthogonal. So we have some orthogonality relationship by Kronecker delta. So delta mn equal to 1 when m is equal to n, and 0 when m not equal to n. If we generalize this interval from minus 0.5 to plus 0.5 to minus L by 2 to plus L by 2, the Fourier series can be expressed in terms of f of x, a0 by 2, the first term of n equal to 0, then n equal to goes from 1 to infinity, and an cosine 2 pi nx by L, and bn sine 2 pi nx by L, where an is given by this integral and bn by the same integral. Okay. So it can also be expressed in terms of the complex notation by consuming both the cosine and sine functions in this manner. So graphically you can see what is happening in this particular case. This is a rectangular function which is can be decomposed into several sine functions in this particular case. Next we come to some properties of the Fourier series. Any function ft can be represented by using Fourier series only when the function satisfies Dirichlet's conditions. That is, the function ft must be periodic and has finite number of maxima and minima. There must be finite number of discontinuities in the signal f of t in the given time interval of time. It must be integrable in the given period. So if it satisfies all these three Dirichlet's conditions, then that function can be represented by using Fourier series. Other properties of Fourier series: linearity property. X of t is the f of xn, and y of t can be represented by the Fourier series. Then the summation of the two multiplied by ax and by can be represented by the following Fourier series. Time shifting property: if x of t can be in the Fourier series pair, and then the time shifting property states the x of t minus t0 can be represented by e to the power minus jn omega naught t0 times f of xn. Frequency shifting property: if x of t and f of xn are Fourier pair, then frequency shifting essentially works in this manner. So e to the power jn omega naught t0 x of t is the Fourier pair of f of x n minus n naught. Time reversal property: x of minus t and f of minus xn are also the Fourier pairs. There are other time scaling properties, differentiation and integration properties, multiplication and convolution properties, and conjugate symmetry properties. They're just given for the completion. Similar properties are also going to be valid. We will see something similar coming up for the Fourier transforms as well. Types of Fourier series: there is trigonometric Fourier series. If sine n omega naught t and sine m omega naught t are orthogonal over the interval t naught and t naught plus 2 pi by omega naught, so sine omega naught t and sine 2 omega naught t forms an orthogonal set. This set is not complete without cosine of n omega naught t, because this cosine set is also orthogonal to the sine set. So to complete this set, we must include both cosine and sine terms. Now the complete orthogonal set contains all cosine and sine terms, that is sine n omega naught t and cosine n omega naught t, where n goes to 0, 1, 2 to infinity. So any function x of t in the interval of t naught and t naught plus capital T, where capital T is given by 2 pi over omega naught, can be represented by this expansion. Therefore x of t can be written as a naught plus summation over n equal to 1 to infinity an cosine of n omega n t and bn sine n omega n t, where t goes from t0 to t0 plus capital T, where capital T is 2 pi over omega naught. In this case, a can be evaluated by 1 over t naught to t naught plus t xt dt. An can be in the similar way represented by xt cosine of n omega naught t and bn as xt sine of n omega naught t dt, integral of t naught to t naught plus t 2 pi over t in the front. There can be similarly exponential Fourier series. where you can express an arbitrary function in terms of exponential series, and you can the Fourier coefficients can be given by 1 over t integral of t0 plus t0 to t0 plus t f of t to the power minus jn omega naught t dt. So let's look at an example. Consider f of t is the sawtooth wave as shown in the figure below, and we have to find its Fourier series. So the figure is evidently forms the function f of t is equal to t, small t, where t goes from minus pi to plus pi, and f of t plus 2 pi is equal to f of t. So the 2 pi is the time period. So by using trigonometric Fourier series, we have a naught 1 over pi integral of t dt minus pi to plus pi, that is equal to 0. An is 1 over pi t cosine nt dt, that is given by the following, and similarly the bn. So if we look into the an and bn evaluation, we can then go back and formulate the f of t as 2 times sine t by 1 sine minus sine 2t by 2, so on. So in the previous example, we just showed one example of a function and how it can be expressed in terms of the Fourier series, where we have a function of sawtooth wave, and we evaluated the Fourier coefficients and then express the function in terms of the series. Before we move on, we just recap what we have learned so far. So we learned, in order to detect the faint signals of the sky from the sky, it is critical to understand the nature and the characteristics of the signal. We learned about the basic nature of signals and the systems, and in our learning of the signal processing techniques, the first one we learned is the Fourier series, and we will be coming to the Fourier transform. Any periodic signal can be represented by the Fourier series. The main drawback of Fourier series is that it is only applicable to periodic signals. It doesn't work on aperiodic signals. So to overcome this shortcoming, Fourier developed a mathematical model to transform signals between time or spatial domain to frequency domain and vice versa, which is called Fourier transform. Now, Fourier transform has many applications in physics and engineering, such as analysis of LTI system, radar, astronomy, and signal processing, etc. So how do you derive Fourier transform from the Fourier series? Consider a periodic signal x of t with period of t. The complex Fourier series representation of x of t is given in terms of the following. X of t is summation over ak e to the power jk omega naught t. Now let 1 over t naught is given as delta f, where delta f is the change of frequency. Then we can define the ak, the Fourier coefficients, in terms of the integral as we did before. So x of t, then if you substitute the value of ak in the original definition of x of t, you get the following expression. So now we take the limit of t tends to infinity, or delta f then goes to df, or infinitesimal frequency interval. In that case, x of t goes to integral of minus infinity to plus infinity. Then within that, another integral of x of t in e to the power minus j 2 pi f t dt, and then there's the e to the power j 2 pi f dt outside as well. Realize this, the central one is actually or can be noted as x of omega, because this is the Fourier transform of x of t. This x omega is nothing but a Fourier transform of xt e to the power minus j omega naught t dt, which is also known as the Fourier transform, and the above equation is known as inverse Fourier transform. So that's how we arrive at the definition of the Fourier transform itself. And x of t and capital X of omega are Fourier pairs, similar like any other arbitrary function of time and frequency. So discrete time Fourier transform, apart from the Fourier transform applicable to continuous signal, it can also applicable to discrete time signal. So for a continuous time signal, it's called continuous time Fourier transform. Discrete time signal, it's called discrete time Fourier signal transform. Sorry. So like it's defined like this: if a sequence DTF of the sequence x of n is given by x of omega, integral of n equal to goes from minus infinity to plus infinity, xn e to the power minus j omega n. Okay, so capital X can be broken up into real and imaginary part because it's a complex quantity. There x real and x imaginary are the real and imaginary part. They can also be broken into cosine theta and sine theta. They follow the simple quadrature rule of x omega's whole square. The norm of that is equal to amplitude of x real square plus amplitude of x imaginary square. They can also be represented as x of omega as x of omega mod e to the power minus j theta omega. The inverse DTFT is also defined as x omega as x of n as 1 over 2 pi integral of minus infinity to plus infinity capital X omega e to the power j omega n d omega. Discrete Fourier transform. Now, if we observe the equations of CTFT and DTFT, that is continuous time Fourier transform and discrete time Fourier transform, the continuous time signal has infinite number of data points for any delta t. This makes impossible to store data in a digital system or some record. This makes CTFT impossible to implement on a machine. Discrete time signal has definite number of data points in a time delta t. This makes a suitable candidate from the perspective of storage. However, DTFT of a discrete time signal results in a continuous spectra in the frequency domain, thereby making it impossible to be implemented on a machine for storage issues. As a result, discrete Fourier transform was also defined, where in the inverse space or the frequency space was also discretized for a discrete signal input. DFT is defined as discrete Fourier transform of x of n is x of k, where n goes from 0 to n minus 1, x of n e to the power minus j k omega n n, where k goes from 0 to n minus 1 and omega n is equal to pi by n, capital N. Here, the Fourier transform is calculated for a set of n equally spaced discrete frequencies or samples. Hence, the sequence x of k is called discrete Fourier transform of the sequence small x of small n. The inverse Fourier transform is also defined as IDFT x of k, that is given by x of n as 1 over n k 0 to n minus 1, x of k e to the power minus j k omega n small n. So just take a look at the Dirichlet's conditions. The function xt has finite number of maxima and minima. There must be finite number of discontinuities in the signal f of t in the given interval of time. It must be absolutely integrable in the given interval of time or sequence. Xt must be bounded. Now, Parseval's relationship states that total energy may be determined by either computing energy per unit time, x of t square, and integrating over total time, or by computing energy per unit frequency and integrating over all the frequencies. So either you would compute this in one Fourier domain or the other, and they're often related as energy density spectrum. Few properties of Fourier transform. Linearity property, axt plus by of t is equal to a, the Fourier conjugate. Time shift property, we have already seen in the Fourier series. The same goes from here. Xt minus t0 is just a phase multiplied by the Fourier transform of the x of t. Similarly, there is a frequency shift property, exactly similar. Time reversal property, time scaling property, differentiation, integration properties, multiplication, convolution, conjugate, and conjugate symmetry properties are all tabulated over here. So let's take a few examples, because we have been discussing about Fourier series and Fourier transform a lot. Let's take a bit of examples so that it may be more clear. So first one, what is the Fourier transform of x of t given by a delta function? Okay, so it's just like an impulse. So if you do the math, it will come out to be a constant. In this case, 1. It's a very powerful transform, because what it says is a impulse in one domain is a constant broadband DC signal in the other domain. We will come back this thing, particularly we will definitely be using this in several derivations, but also we'll coming back to this particularly in terms of interference. When we come to the radio frequency interference signal, we will come back to this particular property and refer to this property quite often. The other one is question number 2. We take a Fourier transform of a rectangular pulse signal where it is equal to 1 between minus t1 and plus t1 and goes to 0 elsewhere. If you do that, you will find that it's kind of sine omega t1 over omega kind of a function. However, there is a little bit of a discrepancy in exactly the discontinuity near minus t1 and plus t1. So if you go back and forth, you see there's a abrupt change in the function caused by this truncation. So there's something called the Gibbs phenomena, which gives rise to this alternating sinusoids, which extends to infinity. Hence it gives rise to this sinc kind of a function, which we say. You can also derive the same thing. So a square wave and the sinc function are kind of Fourier transform of each other, and this is called a duality property. In this question, we have a composite of several square waves, and so if you do the solution using linearity and time shifting properties, you finally can derive the Fourier transform of the given function as x j omega a to the power minus j 5 omega by 2 times sine omega by 2 plus 2 sine 3 omega by 2 by omega. So you have to use both the properties, the linearity property, that Fourier transform of a times fx plus b times gx is equal to a times capital F omega and b times capital G omega. So if you follow that property like we discussed earlier, let's go back and show. If you use this linearity property and time shift property, you can basically get the result of this particular question number 4, because they are composites of multiple rectangular waves. Find the discrete. The next example is find the discrete time Fourier transform xn given by 1, 3, minus 2 and 5. So the DTFT of a sequence is defined as given by this. So if you do the do the series expansion, you finally get you the solution given by x of omega. Question number 6. Let us try to find the discrete Fourier transform of the following. F of t is given by 5 plus 2 of cosine 2 pi t minus 90 degree plus 3 of cosine 4 pi t. Okay, so if you do that, dft is defined by this expression. F of n is summation of small f of k e to the power minus j 2 pi over n small n times k. So if you do the discrete Fourier transform, you finally be able to derive the values of capital F's given the value of the small f's. In f equal to 0 is equal to 8, f of 1 equal to 4, f of 2 equal to 8, and f of 3 equal to 0. If you substitute that, you finally get your answer. Some other standard Fourier pairs. The signum function is represented by sine of t is equal to 1 for t equal to greater than 0 and minus 1 for t less than 0. So it's just a sine function, and that you can express the x of t in terms of that. So where ut is also defined as 1 when t greater than equal to 0 and 0 for t less than 0. So if you apply the Fourier transform, x of omega is given by xt e to the power minus j omega t dt, which is replace the x of t by the sine function. So it breaks up into two different functions because of the sign change for t greater than 0 and t less than 0. And if you do that math, you finally end up having an expression with a limit. So if you put the limit, you finally get x of omega is 2 over j omega. So if you draw the graph, this is how the signum function looks like. Less than 0 it is minus 1, and greater than 0 it is plus 1, so it's a step function. If you do the x of omega, it looks like this. Another one is unit function. So it's 1 for t greater than equal to 0 and 0 for t less than 0. So if this is the plot of that function, if you do the Fourier transform, it goes to f of ut is equal to pi delta omega plus 1 over j omega. So it looks like something like this. We've already shared this standard Fourier transform pair as a first example. So a delta function goes to infinity for t equal to 0, and it becomes 0 for all others. It's like a standard Dirac delta function. And if you do the Fourier transform of that, you finally go to 1. So that's a constant signal. A Gaussian function, if you take a Gaussian function like this with a width e to the power minus a t square, you finally get back a Gaussian function with the width equal to root over of pi by a. Similarly, you can get see exponential function e to the power minus a t times ut, which is the unitary function, unit step signal. If you do that, you finally get the magnitude of x of omega is 1 over square root of a square plus omega square for all values of omega. So a one-sided exponential function equals to this kind of a function. Here are some other list of Fourier pairs for your reference and use. We can also see a constant goes to a delta function, a boxcar function goes to a sinc, a triangle function goes to a sinc square function, a Gaussian goes to a Gaussian. But interesting feature is that a Gaussian with a wider width goes to a narrower width Gaussian in the Fourier domain, and vice versa. A wider Gaussian in the Fourier domain transforms into a narrower. So this lighter curve in the center is a Fourier transform of this broader curve, which is also in light, and the darker curve in this plot is a Fourier transform of the wide Gaussian in the Fourier conjugate space. If you have a sinusoidal function with a single frequency, then you get these two delta functions at those two frequency in -1, -a and +a, and so on and so on. Fourier transform is very, very important because this you can transform the time domain signal v of t into v of frequency. You can also then transform the autocorrelation function into something called a power spectrum or spectral power density function if you do a Fourier transform. So it's very much required in terms of the signals and systems, and we will also be using it more in the signal processing of radio astronomy as well. This brings us close to this particular lecture. I hope you have enjoyed it. As you know, the disclaimer that we have not we have borrowed the materials from many resources, so a reference of them from where we have mainly borrowed the some diagrams, some segments, expressions, etc. So thanks for watching. See you in the next lecture. Thank you very much.